Hey guys, so today I'm going to be breaking down electron domain geometries, and we're going to be using balloons again as a visualization tool for the arrangement and geometry. So molecular geometry describes the shape and orientation of the arrangement of molecules. We know that electron pairs can exist as non-bonding or lone pairs, and also bonding, which is the sharing of electrons through a covalent bond. Now, whether the electrons are bonding or not, they repel each other because we know that like charges repel, opposites attract. And with this basic understanding of how electrons interact with each other as they repel, we can recognize that electron pairs are thus placed as far as from each other. And this is part of the VSEPR theory. And um, in addition, electron pairs, there are also electron domains for this experiment. Um, so they're interchangeable, so we can count and also predict the shape of the molecule, and each geometry has its own characteristics that I will be breaking down. Now, I tried the best of my ability to show you guys the balloons, but I don't have the most nifty hands, so I was able to make some, and I failed making some others. Some others popped while in the process, but given that this is an experiment, ups and downs, failures do happen, and that's all part of the procedure. That's all part of understanding the science. But balloons, they make a great simulation because they're all connected to a focal point, and the way they're tied, it represents the central atom. Electron domain geometry is linear, which I have over here. This was quite easy to do, but in the linear arrangement, there are two electron domains. The molecular shape is linear with a bond angle of 180 degrees. As you can see, it's straight, and it has zero lone pairs. When there are only two balloons, they try to stay away from each other, given the same charges of the electrons, so they're in complete opposite directions. And an example of a linear molecule is carbon dioxide, and in this case, that would be the oxygen, the double bond, the carbon, and double bond oxygen. And linear molecules, they are usually nonpolar. It's starting to get a little tricky, but the next electron domain geometry with three balloons would be the trigonal planar arrangement, and an example of this would be BF3. So with this, as you can see, there are three electron domains, and the molecular shape is a triangular pattern with zero pairs, the bond angles of 120 degrees, and it is nonpolar because the bond polarities cancel each other out. But for the trigonal pyramidal molecule, an example would be NH3. It is polar, and they are polar because the lone pair electron, they throw off the canceling symmetry. And pyramidal, trigonal pyramidal, they have one lone pair. Now it gets a little more trickier with making the balloons, but the following domain geometry is the tetrahedron. As you can see, there are four balloons with a central atom linking all of these bonds. So the tetrahedron has four electron domains with the shape of a triangular pyramid. An example of tetrahedron is the phosphate ion, and the atoms bonded to the central atom, they're located at the four corners of the tetrahedron with 109.5 degrees between them. Tetrahedral molecules, they are nonpolar molecules, given that with zero lone pairs. But as we know with electronegativity, if bond polarities don't cancel out, the molecule becomes polar, like in CH3Cl. This is when I started to encounter some problems, but following the table and the trend with five balloons, three of the balloons, they adopt positions in a trigonal plane, whereas the other two point opposite to each other, like in the linear, which form an axis that is perpendicular to the trigonal plane. So in regards to shape, one atom is present in the center with the other five forming a triangular pyramid. This is called the trigonal bipyramid. And an example of this is phosphorus pentachloride. And following this trend, the trigonal bipyramids, they have 5 electron domains, having 2 bond angles, one being axial equatorial and the other equatorial and equatorial. And it has 3 lone pairs with the linear pair in the axial position. And these lone pairs electrons, they throw off the canceling symmetry of the 5 trigonal bipyramid regions, which make the overall molecule polar. Finally, as things are getting more intricate, with 6 balloons, we have an octahedron or a square pyramid. And an example of octahedron is fluorite. It has 2 square pyramids back to back, with each square pyramid with 4 faces. And it has, as we are going up, it has 6 electron domains. And since the domains from non-bonding pairs exert larger repulsions than the bonding pairs, they occupy equatorial positions in a trigonal pyramid. So octahedron has 4 bonding pairs and 2 lone pairs, and it can be square pyramidal or square planar. The octahedral molecule is nonpolar. So I'm sorry it got a little confusing towards the end, especially without the visual demonstrations in the balloons. But this week's experiment, it really showed through balloons the interaction and the shape and arrangement we're seeing as every time we add a balloon, how the bond angles are affected. We see how the repulsions can be demonstrated, and also as a result of the molecular geometry, how the characteristics are exhibited through lone pairs, through shapes, electronegatively, polarity. These are all concepts that we build upon from this course. But in conclusion, this was a pretty straightforward experiment. I obviously mentioned earlier, and as you saw, that I had trouble with building some of the more complex molecules, but that goes to show the nature of an experiment. And as always, by increasing more trials, maybe blowing the balloon smaller, might have been more easier, and how you tie them can always show the dynamic and nature of molecules. But that's it for this week. Thanks for watching, and I hope that I was able to break down all the types of molecular geometries and their characteristics.